So, the next talk is titled A Comparative Study of Secondary Indexing Techniques in LSM-based NoSQL Databases, and the talk will be given by Muhiuddin Abdul Qader.
Thank you. So I'm Muhiuddin from UC Riverside. So the motivation behind our project is NoSQL databases are very popular because they provide high write throughput and fast lookups on primary key. Because that's why these are very popular for big data applications. Nowadays, NoSQL databases also support secondary indexes. For example, if you store tweets, where your primary attribute is tweet ID and you have a user ID as secondary attribute, you want to efficiently return a query like return all tweets where user ID equals to, for example, Donald Trump. Now, different NoSQL systems support different secondary indexing strategies, and it is very hard to compare their performances because no system supports all of them. And there's been a very limited research comparing these strategies. So we implemented 5 secondary indexes on top of LevelDB, which is Google's open source key value store. So we call it LevelDB++, and this test bed allows us to compare performance between all of them. So the contribution is we present a taxonomy of secondary indexes broadly split into 2 classes. First is embedded index, which actually are lightweight filters embedded inside the primary data table. The examples are Bloom filter and zone maps. And there are also another classes, standalone indexes, which is separate data structures. And we implemented 3 standalone indexes named eager, lazy, and composite. We actually couldn't talk about the composite index here in this session, but please feel free to read our paper, and you can also come to the poster session. Also, we theoretically analyze all of the indexing strategies costs. We perform extensive experiments on various workloads. So these are the set of the operations that a typical NoSQL system support or want to support. So first 3 are get, put, and delete. These are operations on primary key, which are typically very efficient in key value stores. The last 2 is lookup and range lookups on secondary attribute, which typically NoSQL systems want to support, but they are slow. So our focus is on these 2 operations, and we want to make it efficient, but without having too much overhead on the top 3 operations. So one of our previous presenters already explained what is LSM. So LevelDB is a LSM-based database, which has level-based storage organizations. And you can see that in SS tables are organized into different levels, and inside one level, we have non-overlapping primary key ranges. So LevelDB actually already supports embedded indexes like Bloom filters and zone maps for primary attribute. So we simply extended these indexes for secondary attributes too. For example, this is actually SS table file format, where we can see that they are divided into fixed size data blocks, and at the end we have Bloom filters and zone maps for primary keys. Here you can see that we just extended these blocks for secondary attribute. Now, zone maps, which actually min-max range of key for entries in each blocks, but they may only good for time correlated attributes. By time correlated, we means the attribute values increases or decreases by time. And also Bloom filters can support only point lookups. They cannot support range queries. For that, to support embedded index, we considered them together and we implemented them together. Now, as there is no separate structure to maintain, there is very little impact on writes, and it is maintained during background compaction. So the range lookup and lookups, it search in SS tables starting from level 0 to lower levels. For each block of an SS table, we check the Bloom filter and zone maps. If true, we fetch the block and search for secondary key. Another tab is standalone index. Here we have like a separate level DB database holding lists of primary attribute values. So the challenge is here is when we insert a new record, how to update the secondary posting lists. Now, there is two strategies here we discuss. One is eager update and lazy update. Here's an example of the eager update. So suppose this is the state of the database. Now, if we have a new record coming where T3 is the primary key and user ID U1 as the secondary key, what eager update will do, it will read the current list of U1 from the database, which is T2 and T1. It adds T3 to the list and write back to the database. So it will look like this. So the lookup will simply read from the top level, which is here in T3, T2, and T1. So after some level of compaction, we expect these older lists to be removed. The next is lazy index, where we do not issue any reads. We simply write U1 and T3 to the database. It will look like this. Now we can see that we have fragmented secondary lists throughout these different levels. So lookup or range lookup has to go through different levels. After some level of compaction, we expect the compaction to merge the list, so the lookups are faster. So the eager index is faster for writes, but faster for lookups, but it's slow for writes. But the lazy index is faster for writes, but the lookups will be slower. So here's some results. So we use two indexes, user ID and creation time from Twitter database. Now, if we see the index size, lazy has the highest index size, where embedded index is very smaller. It's close to having no index. If we see the insertion time, eager actually performs very poor because, as we can see, we are reading from the database, and also there's been a very high write amplification cost, and where we can see that embedded index is very fast. Now we have some more interesting observations regarding lookups and range lookups, but for time constraints, we won't be able to show here. But we can show a decision tree from these observations. We conclude some decisions like which scenarios actually prefer which secondary indexes. So here, example is like if we have like index attribute which is time correlated, or we have a space constraint, or the application has very high ratio of writes to lookups, it is better to use embedded index. Otherwise, it is better to use like the lazy index. For some cases, like if we want like top K results, it is better to use composite index. To learn about composite index, please come to the poster session. So thank you for listening. Any questions?
This is just a clarification question. You mentioned lazy index, you mentioned the eager index, you didn't mention composite index, and then in your conclusion you started to talk about composite index, which is, so what is composite then?
So comparison index will look like this. Actually, we have it here, but we couldn't present it. Okay. So composite index actually is a hybrid. So the key will be the primary key and the secondary key together, and value will be null. So this is like a composite key, and this is the state of, will be the state of the secondary table.
Got it. Thank you.
Got it?
Okay, let's thank the speaker once again. Active and visualized exploration, and Tao Guo will be giving the talk.
Okay. So our work is basically to help users to understand and to know the spatial data before they are ready to use them. So the problem here is now we have, sorry. So the problem here is that we have a lot of data now. So when helping users to explore the data, the most straightforward way is to put them on a map to visualize them. But the problem here is that if we put a lot of data on a single map, they may overlap each other, and they are not read-friendly to the users. So in this work, we aim to select a very small collection of data such that these data are not overlapping with each other, and they are very easy for users to read them. And the most important is that the small data set can represent the whole data collection as much as possible. So we can also let the users to click one of the data. So here is an example. The user can like to click. There's a restaurant, steakhouse, and at the same time we can show more the similar results here on the map. So in this way we can better to help the users to explore the data site. So so the problem here is that when playing with the maps, we should consider the consistency. For example, we have shown, this is an example from Google Map, and we have shown some items on the map, for example, the New York Stock Exchange here. By zooming in the map, something already shown on the map should be visible, and we should maintain the consistency of the after the user's operations. So in this work, we consider three types of interactive operations: the zoom in, zoom out, and panning. For the zoom in operation, something is already shown on the map should be visible after zoom in. And for the zoom out, some item that are not visible should be also not visible after zoom out. And similarly for panning, and the overlap space should remain consistent. So our work has the following features. So we first consider the moving and zooming and movement consistency, and we also consider the visibility constraint. It means that the results shown on the map should not be too close to each other. And we want the result to be representative. It means the result should represent the whole data set as much as possible. And in this work, we also consider various types of geospatial data. It may include the documents, the images, and in this way, we need to support, we use a very general similarity function, so we can support different types of the data. So we also want to have a very efficient algorithm such that the problem is online, so the user can get the results immediately. So compared to some existing works, our work is the first to support all the features. So given this concept, the geospatial data we are studying about is consists of three components. It has the location, it has a weight of importance, it also has a set of contributes. So for the different type of the spatial data, we can use the different attributes, and in this way we can compute the similarity between each pair of the objects. So for example, for the Twitters, the attributes can be like the textual content, the post user, the time spec. So we already know, given the two objects, we can compute the similarity. But given one object and a set of objects S, so we use the maximum similarity between one object O and another object in the object S. The intuition behind here is that if this object S can represent the object O, it means that the similarity between O and some object in S is very high. So when extend this one object to all the objects, we have the following objective function. And in this work, we want to maximize this objective function as much as possible. So here we also consider the weight of each object here. So given this concept, we have proposed a spatial object selection problem. So the problem is to select a subset of object S which is size of k, from a geospatial object size data. So we want this result to be meet the map constraints. So in the results, each pair of the objects should be larger or equal to a given parameter. So we want to the result to maximize the object function as much as possible. So when considering the interactive operations, the problem actually is very similar, but we also consider two more concepts. The one is that we should consider the candidates that we can choose from. And another is that we should consider the set of objects that are always visible before and after our operations. So given that we come to a greedy solution, we'll first prove that the object function is submodular, such that we give the idea behind that is that we compute the objects that contribute to the representative score. And in each round, we choose the object that can increase the score to the most. And prove that this algorithm has a constant approximation ratio. And we also do the laser forward to optimize the time. And for the interactive version of this problem, we also notice that some computation can be done before the user's next operation. So we use the perfection technique to do some pre-computation. So we also do the sampling extension when the set of data set is quite large. So our experiments, we are using 3 different real-world data sets, and we compare with 5 baselines. So we can see that our algorithm outperforms the 5 baselines in terms of the runtime and the score. And we can also see that our sampling-based algorithm is a little bit, the quality of our sampling extension is a little bit faster, but the quality is nearly to the greedy algorithm. So here is an interesting case study. So here we are given some objects, and we use the distance as the similarity function. So we aim to see that by only see the selected subset of data, we can know the distribution of the original data set. So we can see that the second picture is the result picked by our algorithm, and compared to the random and the other baselines, our problem can somehow represent how the data is distributed in the space. And that's all. Yeah. Thank you.
Questions? Come to the microphone.
So, thank you so much for the presentation. So I was wondering if you can go back to the problem definition where you mentioned, and next slides, and then the next one, page 9, I think maybe. Again, next one. So sorry about that. I didn't remember the exact page number. Oh, yeah, the previous one. Yeah. So here, how do you define the zeta? So
actually, it's a given parameter.
So given by the user?
Yes, given by the user. Actually, it depends on your different application. If you like to visualize them on a mobile phone, the threshold may be quite small. But if you like using a web browser to look into this application, it will be different. So we think it's like a given parameter. So
so is there a way you can help the user to determine the best data for their use case?
It's a very good question. Actually, we you may have to let the user to.
Yeah. So maybe give them hints, like some ideas of how to decide this parameter.
Okay. So one of the ideas is that because we can give because we are using different devices to visualize the results. So one way is that we can use some certain percentage of the your resolution. For example, you are giving different, you have a big screen or you have a small screen. So you have some specific percentage of the screen to set this distance threshold. Yeah.
I see. But so in case of mobile phones, if the screen has some kind of super sampling mechanism, like the retina display that Apple used, so it might be difficult for a user to come up with the CTR.
Yes. So that's why we we also have the set K to control the number of results shown on the map. So both of them can control the result the final results. Yeah.
I see. Thank you so much.
Yeah, thank you.
Okay, let's thank the speaker once again.